Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of electronic circuit, and today we are discussing the supercapacitors. And we discussed about the supercapacitor in history, how we design it, how we store it, the energy in the supercapacitor. Now what are the principles of the storage of the energy in the supercapacitor. Now we discuss the type of supercapacitor. Here the supercapacitor are also referred to as a gold capacitor, power capacitor, ultra capacitor or the supercondenser. On the basis of their charge storage mechanism, they are classified into the three types. One is the supercapacitor, one is the double layer capacitor, second is the pseudo capacitor, and third is the hybrid capacitors. So the double layer capacitor, pseudo capacitor, which are the double layer using the activated carbon and carbon suit in the preparation, while if we talk about the pseudo capacitor, it uses the conducting polymers and the metal oxide. Another type of the supercapacitor is a hybrid capacitor, which is combination of the double and the pseudo capacitor, and it uses the various electrodes and various composites for the preparation of the supercapacitors. And now if we talk about the double layer capacitor, which is the one form of the supercapacitor, it uses the activated carbon electrodes or derivatives of the carbon with much higher electrostatic double layer capacitance than that of the electrochemical pseudo capacitor. If we talk about the pseudo capacitor, with the transition metal oxide or the conducting polymers electrode with a high electrochemical pseudo capacitance are used. If we talk about the hybrid supercapacitor, then we use with the this is also the asymmetric electrodes, and one of which exhibit the mostly electrostatic and other mostly electrochemical capacitance. That example are the lithium ion capacitors. So because double layer capacitance and the pseudo capacitance both contribute inseparably to the total capacitance value of an electrochemical capacitor, a correct description of these capacitors only can be given under the generic terms, like the concept of the supercapacitory and the super battery have the recently proposed to better represent their hybrid devices, where we use the double layer as well as the pseudo capacitor. So the supercapacitory and the supercapacitory, so these are recently proposed for the better responses, and these are the hybrid devices, and they behave more like the supercapacitor and the rechargeable battery respectively. Now the capacitance value of the supercapacitor is determined by the two storage principle. Number one, if we talk about the storage principle, then the double layer capacitance electrostatic storage of the electrical energy achieved by the separation of the charge in the Helmholtz double layer at the interface between the surface of the conductor electrode and the electrolytic solution, that is electrolyte. The separation of the charge distance in the double layer is on the order of the few angstrom, that is 0.3 to 0.8 nanometer, and is static in the origin. So double layer capacitor are the static in nature. Pseudo capacitor electrochemical storage of the electrical energy achieved by the redox reaction. In the previous one, it is used the Helmholtz double layer at the interface between the surface of the conductor electrode, but here the electrochemical storage of the electrical energy achieved by the redox reaction. Electroabsorption or the intercalation on the surface of the electrode by specifically absorbed ions that result in the reversible Faradaic charge transfer on the electrode. The double layer capacitance and the pseudo capacitor both contribute inseparably to the total capacitance value of the supercapacitor. How the ratio they can vary greatly depending upon the design of the electrode and the composition of the electrolyte. So, pseudo capacitance can increase the capacitance value by as much as factor of the 10 over of the double layer by itself. So, electric double layer capacitors are electrochemical capacitors in which the energy storage predominantly is achieved by the double layer capacitance. As the name suggests, it is using the double layer capacitance. And this uses the double layer capacitor together with the pseudo capacitor as a part of large family of the electrolyte electrochemical capacitor that will becomes under the supercapacitor, and these are also called the ultra capacitor. So, now we discuss the electrostatic double layer capacitor. This type of capacitor works on the charge storage mechanism, where a charge is physically stored on the surface of the electrode without causing any irreversible chemical reaction by the formation of an electrical double layer. So, here we are using the electrical double layer. Usually the carbon based electrode are used in supercapacitor, which are separated by a dielectric substances that acts as an insulator and possesses electrical properties that eventually affect the performance of the superconductor. So, the charges are electrostatically stored in the supercapacitor. So, in this double layer, the charges are electrostatically stored in the supercapacitors. An electrical field is generated at each electrolyte as soon as the voltage is applied across the terminal, with the leads to the polarization of the electrolyte. Then what happened? Then as a result of which ions diffuse through the dielectric to the porous electrode of the opposite charges. This is very important point. When we apply the voltage, then the voltage across the terminals which leads to the polarization of the electrolyte, and as a result of which ions diffuse through the dielectric to the porous electrode of the opposite charges. In such a way, the formation of electric double layer takes place at each electrode, and this result in the increased surface area of the each electrode and decrease the distance between the electrode. And in this manner we can get, now you see clearly on the screen that this is a electrolyte, or we are having a two electrodes, one is current collector, right hand side we also have a current collector, and we are using the active porous electrode material, and we have a positive and negative ion, and when the voltage applied there is a separator, then that it will collect towards the electrolyte. So, this is the one of the schematic diagram. Now, the amount of charge in the electrode is matched by the magnitude of the counter charges in the outer Helmholtz plane. So, this double layer phenomena stores the electrical charges as in the conventional capacitor. The double layer charges forms a static electric field in the molecular layer of the solvent molecule in the IHP that correspond to the strength of the applied voltage. So, the double layer serves approximately as a dielectric layer in a conventional capacitor and with the thickness of a single molecule. Thus, the standard formula for the conventional plate capacitor can be used to calculate their capacitance. You all know that C is equal to epsilon A by D. So accordingly, the C is the greatest of the capacitor, greatest in the capacitors made from the material with the high permittivity, that is epsilon. Large electrode plates surface area, that represented by the A, the smaller distance between the plate, that defined by the D. So as a result, the double layer capacitor have much higher capacitance value than the conventional capacitors, arising from the extremely large surface area of the activated carbon electrodes and the extremely thin double layer distance on the order of the few angstrom in order of the Debye length that we will define. And moreover, the ability of the electrodes to accomplish pseudo capacitance effect by redox reaction, intercalation or electroabsorption. So strongly depends upon the chemical affinity of the electron material to the ion absorbed on the electrode surface as well as on the surface structure as the dimensions of the electrode pores. Now in the pseudo capacitors, material exhibiting the redox behavior. The previously Helmholtz we use, but here we use the redox behavior in the pseudo capacitance. So the materials exhibiting the redox behavior for use as electrodes in the pseudo capacitor are transition metal oxide like RuO2, IrO2, MnO2. These are the transition metal oxides. Or we can use the polymer also in this, inserted by doping in the conductive electrode material such as the active carbon as well as the conducting polymer such as the polyaniline or its derivatives of the polythiophene covering the electrode material. The amount of electric charge stored in the pseudo capacitor is linearly proportional to the applied voltage. In the pseudo capacitance, the electric charge stored is linearly proportional to the applied voltage. The unit of the pseudo capacitor is a farad and same as the capacitance. So although the conventional battery type electrode material also use the chemical reaction to store charges, they show very different electrical profile as the rate of the discharge in the limited by the speed of the diffusion. Like assuming that the minimum distance between the electrode and the charge accumulating region cannot be less than the typical distance between the negative and positive charges in the atom, approximately 0.05 nanometer, and general capacitance upper limit is approximately 18 microfarad per centimeter square. So that has predicted for the non-faradic capacitors. The main drawback of the carbon electrode of the double layer supercapacitor is small value of the quantum capacitance, which act as a series of the capacitance of the ionic space charges. So further increase the density of the capacitance in the supercapacitors can be connected with increasing of the quantum capacitance of the carbon electrode nanostructure. Means if we use the carbon, so it is necessary to increase the quantum capacitance of the carbon electrode nanostructures. In the pseudo capacitors, that is also called the faradic supercapacitor, as they use the redox active materials. So these devices uses the electrodes made of the redox active materials. What are these? As we discussed, that they uses the metal oxide and the conducting polymers. Polymer may be of the any type. So these electrode store charge through the reversible faradic reactions mechanism near the electrode or at the electrode surface where the charges are transferred across the metal electrolyte interface. So you see on the screen here the metal oxide are used. Now you see the pseudo capacitance with the specifically absorbed ions. So they are the electrolyte you see on the screen. Left hand side is having the collector, and there is a inner Helmholtz plane. Now here that we are doing the solvated cations, and there is a polarized solvent molecules. Specifically we are having the absorbed ion, that is a redox ion. So, this is the schematic diagram of the pseudo capacitor. Electrode with the supercapacitors, we use the MnO2 and RuO2 are the typically materials that use as the electrodes for the pseudo capacitors, since they have the electrochemical signature of the capacitive electrode, that is linear dependence on the current versus voltage curve, as well as the exhibiting the AIC behavior. So, additionally the charge storage originates from the electron transfer mechanism rather than the accumulation of the ions in the electrochemical double layer. So, that is why pseudo capacitor works faster as compared to the double layer capacitor. So, the charge storage originates from the electron transfer mechanism rather than that of the accumulation of the ions in the electrochemical double layer. Pseudo capacitors were created through the Faradic redox reactions that occur within the active electrode material. So, more research are focused on the transition metal oxides such as MnO2, since transition metal oxides have a lower cost compared to the noble metal oxide such as RuO2. However, the charge storage mechanism of the transition metal oxides are based on the predominantly or the pseudo capacitance. So, two mechanisms of the MnO2 charge storage behavior were introduced. The first mechanism implies the intercalation of the proton, that is defined by H positive, or the alkali metal cations C plus in the bulk of the material upon the reduction, followed by the deintercalation upon oxidation. As you see, MnO2 plus H plus C plus E, that is MnOOCH, that is taken from the reference. And the second mechanism is based on the surface adsorption of the electrolyte cations of the MnO2. You see, MnO2 surface plus C plus E negative, then MnO2 plus surface. Not every material that exhibit the Faradic behavior can be used as an electrode for the pseudo capacitor, such as if we talk about the NiOH2, since it is a battery type electrode, linearly dependence on the current versus voltage curve. Another type of capacitor that comes under the asymmetric capacitor is the hybrid capacitor. We already discussed in the previous lecture that what is the hybrid capacitor, but here we discuss in detail. This super capacitor can also be made with the different materials and principles of the electrodes. If both these material use fast capacitors type reaction capacitance or the pseudo capacitance, the result is called the asymmetric capacitor. So, in this asymmetric capacitor we have hybrid capacitor, and these capacitors have adopted both the mechanism of EDLC double layer capacitors and the pseudo capacitor, and these hybrid capacitors are composed of the electrodes with the different characteristics based on the chemical as well as the electrical mechanism. That characteristics we have defined in the previous lecture, that what are the characteristics of these three type of capacitors. So, that we can see from that lecture, but here we can see that these hybrid capacitors are composed of the electrodes with the different characteristics based upon the chemical as well as the electrical mechanism. As a result, one electrode exhibits electrostatic capacitance and other provides the electrochemical capacitance. Means we have both the electrostatic as well as electrochemical capacitance in the hybrid capacitor. The advantage include higher operating voltage, that is the 3.8 volt maximum, and increased the capacitance and the energy density. So, it worked faster or more efficiently than that of the previous capacitors. So, the number of newer capacitor are the hybrid capacitor. Only the one electrode uses a fast reaction, that is a capacitance or the pseudo capacitance, and the other using only the battery like material. For example, an EDLC anode can be combined with an activated carbon NiOH2 cathode, the later being a slow Faradic materials. So, CV and GCD profile of a hybrid capacitor have a shape between that of the battery and the supercapacitor. So, more similar to that of the supercapacitor. Hybrid supercapacitor have much higher energy density but have inferior cycle life and current capacity owing to the slower electrode. You see on the screen that this is the hybrid capacitor, that is anode cathode, and there is a separator, and in between that we have a electrolyte, we have a solvent molecules also. So, what are the properties of superconductors? Some properties of the supercapacitors are here. We discussed that the supercapacitor have a long cycling time with a high cyclic efficiency like 84 to 90%, and this is considered to be one of the most important feature of the supercapacitor. It means it is having the high cycle efficiency that comes under the 84 to 97, and this is considered to be one of the most important features. Supercapacitors have the capacitance ranging from the 1 millifarad to the 10 kilofarad. Supercapacitors have a high energy density of up to the 10 watt hour per kilogram. So, there is a less potential for the pollution in the supercapacitor as no heavy metals are used in their development. Another important property is the charge discharge time of the supercapacitor ranges from millisecond to the few second. Supercapacitors come up with the property of the longer service life of the 10 to 15 years. As supercapacitors have higher capacitance with lower voltage limit, and they are preferred over the batteries and conventional capacitors. What are the application of the supercapacitors? Nowadays, supercapacitors are used in many electronic, mechanical as well as the electrical devices. So, applications have supercapacitors have advantages in the application where a large amount of the power is required for a relatively short time, where a very high number of the charge discharge cycle or a longer lifetime is required. So, typically applications range from the milliamp current to the milliwatt of the power for up to the few minutes to the several amps current or the several hundred kilowatts power for much shorter period. Supercapacitor do not support alternating current application. In the consumer electronics, we use the supercapacitor. So, this application with the fluctuating loads such as laptop, computer, PDA, GPS, portable media players, handheld devices and the photovoltaic systems. Supercapacitors can stabilize the power supply. Supercapacitor deliver the power for the photographic flashes in the digital camera, LED flashlight that can be charged as much shorter period of the approximately of the 90 seconds. Some portable speakers are powered by the supercapacitor. So, a cordless electric screwdriver with the supercapacitors for the energy storage has about the half the run time of the comparable battery model. So supercapacitor without the cordless can work better, but can be fully charged in the 90 seconds and retains 85% of its charge after their 3 month left ideal. Means the charging discharging capacity of the supercapacitors are more as compared to the other. Moreover, the power generation and the distribution, where we use it in the grid power buffering. So, nowadays numerous non-linear loads such as electric vehicle charges, high electrical vehicle charges, air conditioning system, advanced power conversion system cause a current fluctuation and the harmonics, where we use this supercapacitor. The current differences create the unwanted voltage fluctuation and therefore the power oscillations on the grid. So, the power oscillations not only reduce the efficiency of the grid, but can cause the voltage drop in the common coupling bus and the considered frequency fluctuations throughout the entire system. So, to overcome this problem, supercapacitors can be implemented as an interface between the load and the grid to act as a buffer between the grid and the high pulse power drawn from the charging station. Another important application where we use the supercapacitor is the low power equipment power buffering, like rotor with the wind turbine pitch system, where we use the supercapacitor. This supercapacitor provide backup or the emergency shutdown power to the low power equipment such as RAM, SRM, microcontrollers and the PC cards. They are the sole power source for the low energy applications such as the automated meter reading and equipment or even the notification in the industrial electronics. Supercapacitor buffer power to and from rechargeable battery, that is mitigating the effect of the short power interruption and the high current peaks. The batteries kick in only during the extended interruptions. So, its main power or a fuel cell fails, which lengthens the battery life. So, supercapacitor provides the backup power for actuators in the wind turbine pitch system, so that the blade pitch can be adjusted even if the main supply fails. In this the supercapacitors use also in the voltage stabilization. So, supercapacitor can stabilize the voltage fluctuations for power line by acting as dampers. Wind and photovoltaic system exhibit the fluctuating supply evoked by the cloud that supercapacitors can buffer within the millisecond. Another application is a microgrid. A microgrid are usually powered by the clean and renewable energy. Most of this energy generation, however, it is not the constant throughout the day and does not usually match demand. So, supercapacitors can be used for microgrid storage to inject power when the demand is high and the production dips momentarily, and to store the energy in the reverse condition. And they are useful in their scenario because microgrids are increasingly producing the power in the DC, and the capacitor can be utilized in both DC and AC application. So, supercapacitors work best in conjunction with the chemical batteries, and they provide the immediate voltage buffer to compensate for quick charging. Power leads to their high charge and discharge rate through an active control system. Once the voltage is buffer, it is put through an inverter to supply AC power to the grid. Supercapacitors cannot provide the frequency correction in this form of directly to the AC grid. Another type of application is the energy harvesting, where we use this supercapacitor. We use this supercapacitor in the batteries, that are the ultra batteries, and we use this supercapacitor in the medical for the defibrillators, and where they can deliver the 500 joules to shock the heart back into the sinus rhythm. Moreover, we use it in the military for the low internal resistance support application that requires a short term currents, and military application we use it in the transport also. Then thank you very much. There are many more application of this. So up to now we have discussed the supercapacitors and its type and its application and its property. Thank you very much.